HeatCond2D is an app that is used to estimate the temperatures within a section based on the 2D explicit finite difference method with quadrilateral meshes. The app has a meshing feature to automatically mesh a section. Certain features shown in this tutorial are only available in the Pro version. In the section page, a section can be created for the meshing to be carried in the thermal page. The thermal page is accessed by toggling on the thermal toggle button. When the thermal page is toggled off, the section page is shown. A section can be created either by using manual input of coordinates or templates. For example, to create a rectangle section with a width of 100 mm and depth of 200 mm manually using the coordinate input, select Solid in the Element tab and choose mm in the input unit selector. Next, enter the following in the X and Y input fields and tap on the plus icon after entering each set of coordinates, 0.1, 0 and 0. 0.2, 100 and 0. 0.3, 100 and 200. 0.4, 0 and 200. 0.5, 0 and 0, or alternatively tap the plus icon to close the section. Tap on the New button to start a new project. A dialog box notifying that all current data will be deleted will appear. To cancel the Create New action, tap on the Cancel button. In this example, we will proceed to create a new project, therefore tap on the OK button. Please note that the input unit selector has been reset to the default of meter if the metric unit system is selected in the settings page. If the imperial unit system is selected in the settings page, the input unit selector will reset to foot. In the input unit selector, choose millimeter. To create the same rectangle section using templates, select the light panel icon to access the section template. In the section template, there are a number of pre-built templates to create a section. For this example, tap on the rectangular section button, which will bring up the rectangular section template. In the rectangular section template, enter the following. Section width, B0 of 100. Section depth, D0 of 200. Leave the void width B1 and void depth D1 empty as there is no void to create in this example. Each section must have the solid element as the main building block. Therefore, leave the outer element as solid. Tap the scribble button to create the section. Continuing with this section, we will add a circular void to it. The center of the circular void will be located X coordinate of 50 and Y coordinate of 150. The radius of the void will be 30 mm. For this example, we will set the void as void 2. Select void 2 on the Element tab. Tap the quarter square icon to access the shape template. The shape template has pre-built templates for rectangle, circle and polygon. Tap on Circle in the Shape tab and enter the following: reference X coordinate of 50. Reference Y coordinate of 150. Leave the thickness T as empty. Enter a radius as 0 of 30. Leave alpha as 0 and beta as 360. These parameters are used to generate a full circle. Tap on the scribble icon to generate the circle. Next, we will modify the section, specifically the right-hand corner point. In the section page, toggle on Modify. The plus icon will change to an eraser icon. Toggle on the Mark Toggle button and Point Toggle button. Tap on Point 2 on the chart. Change the X coordinate and Y coordinate fields to 100 and 100. Tap on the eraser icon to proceed with the change. Toggle off the Modify Toggle button and tap on Point 1 on the chart. Ensure that in the list Point 1 is highlighted and not Point 5. In the X coordinate and Y coordinate fields, enter 50 and 100. Tap on the plus icon to add the new point. Tap on Point 1 on the chart again. This time, in the X coordinate and Y coordinate fields, enter 50 and 0. Tap on the plus icon to add the new point. Toggle off the Mark Toggle button and Point Toggle button. Next, the section will be rounded at each corner. The 6 corners will be rounded. Tap on any one of the corners and tap compass icon to access the rounding page. In the rounding page, enter a radius R0 of 25. Leave the rounding type as concave and angle type as minor. Tap on the scribble icon to round the selected corner. If a rounding occurs, tap on the undo icon and start the rounding steps again. Repeat the rounding steps for all the other corners. Next, the section will be rotated 90 degrees in the clockwise direction. To rotate the section, the solid element and void 2 element are to be rotated separately around a reference point. Let x-coordinate and y-coordinate of this reference point be 0 and 50. First tap on Solid on the Element tab. Toggle on the Modify Toggle button. Long press on the chart until the line of the solid element changes and the point ID field shows solid. Tap on the Rotate icon to access the Rotation page. Tap on Clockwise in the Direction tab. Enter a rotation angle of 90 degrees. In the Rotation Point selector, select User Defined. In the X-coordinate and Y-coordinate fields, enter the reference point coordinate of 0 and 50. Tap the rotating pencil icon to rotate the solid element. With the Modify Toggle button still toggled on, tap on Void 2 in the Element tab. It is noted that the Void 2 is highlighted to show that the Void 2 element is outside the solid element. The Void 2 element should be selected. If the point ID field shows Void 2 instead of a number, it shows that the Void 2 element has been selected. If the point ID field shows a number, then long press the chart until the line of the Void 2 element changes. Tap on the Rotate icon to access the Rotation page. Tap on Clockwise in the Direction tab. Enter a rotation angle of 90 degrees. In the Rotation Point selector, select User Defined. In the X-coordinate and Y-coordinate fields, enter the reference point coordinate of 0 and 50. Tap the rotating pencil icon to rotate the Void 2 element. The section should be 90 degrees in the clockwise direction to its original position. Toggle off the Modify Toggle button. Once the section is created, the heat transfer modeling can be carried out. To create a heat transfer model, the section will need to be meshed and boundary conditions applied to the model. Toggle on the Thermal Toggle button to access the thermal page. It is important to note that the undo and redo features are not available in the thermal page. First, tap on the Mesh icon to access the Mesh Properties page. The Mesh Properties page contains the Quad Section button, Mesh Configuration button, Time Step and Material Properties. Tap the Quad Section button to access the Quad Section page. The Quad Section page allows the use of symmetry to model a section. Where a section is symmetry about the X and Y axis, either section quadrant can be selected. Where the section is symmetry about either the X axis or Y axis, either section half can be selected. In this example, there is no symmetry about either the X-axis or Y-axis. The symmetric test will indicate if a section is likely to be symmetry or otherwise. Tap on the Cancel button to return to the Mesh Properties page. Next, well mesh the section. Tap on the Mesh Configuration button to access the Mesh Configuration page. In the Mesh Configuration page, the size of the meshes in the X and Y directions are specified. It is recommended for the mesh size in the X and Y directions to be similar if not equal. The mesh size in the X and Y directions are automatically calculated and shown. However, these mesh sizes can be changed according to suitability. The mesh symmetry can be selected about any of the axes. Select from either No Preference, About Y-axis only, About X-axis only or About Y and X-axis. The modified mesh size for each of the X and Y directions is also calculated based on the section X and Y dimensions. In the selected mesh size, the trial mesh size or modified mesh size can be selected. For this example, the trial mesh sizes and the selected mesh size will be unchanged. Tap on the Generate button to proceed with the mesh sizes and return to the Mesh Properties page. In the Mesh Properties page, there are material properties for the solid, Mat 2 and Mat 3 elements. Only the material properties for the element in use would need to be specified. For this example, only the solid element is used. In the library selector, select concrete. Material properties can also be saved after input or a saved material properties file open. To save a material properties file, tap on the solid material button to access the material files. Tap on the Save button and enter the material name. For this example, we will enter a file name of test material. Then tap the Save File button to return to the Material Files page. Tap the cross icon to return to the Mesh Properties page. To open the Saved Material Properties file, select User Defined in the Library selector and tap on the Solid Material button. Tap on Test Material and then tap the Open button to use the Saved Material Properties file and return to the Mesh Properties page. For this example, there are stability checks shown by the 4 green ticks are maintained. If steel is selected for the solid material, for red crosses would be shown. If this occurs, reduce the time step until 4 green ticks are shown. It is noted that the choice of time step could increase the actual run time of the heat transfer analysis. Therefore, judgment to be exercised when specifying the mesh size and time step for a particular material. Under the solid material properties, in the library selector, select concrete. Tap on the OK button to generate the mesh and return to the thermal page. Toggle on the Node Toggle button to show the external nodes. With the Group Toggle button off, tap on an external node to show its data. The node data shows X and Y coordinates of the selected node, position of the node in the row and column, node type and applied boundary condition. Toggle off the Node Toggle button and toggle on the Mesh Toggle button. With the Group Toggle button off, tap on a mesh to show its data. The mesh data shows the material number and properties. Next, the boundary conditions for the model will be specified. Toggle on the Node Toggle button to show the external nodes. Double tap on the node text of the Node Toggle button to show the internal nodes. For this example, no boundary conditions will be applied to the internal nodes. So double tap on the node text of the Node Toggle button again to hide the internal nodes. A fixed temperature of 100 degrees Celsius will apply to the around the void and a time temperature exposure profile will be applied to the other external nodes of the section. Toggle on the Group Toggle button. Double tap the group text of the Group Toggle button to select all nodes. The selected nodes will be highlighted. Tap on the boundary icon to access the Node Boundary Conditions page. The Node Boundary Conditions page allows a user to apply different exposures to the nodes. For this example, a surface temperature profile will be applied to the external nodes of the section. From the Exposure Type selector, select Surface Temperature. From the Exposure Profile selector, select Applied Temperature. The applied temperature will be defined later in the Exposure Temperature Profile page. Where an ambient temperature is selected, this temperature is defined in the Simulation Data page. As the only one radiation and convective exposure for gain and loss parameters can be specified in the Simulation Data page, varying the parameters can be done by specifying different radiation and convective factors to the emissivity and convective heat coefficient. This is done by tapping on the radiation gain, radiation loss, convective gain, and convective loss texts to access the factors. The factors are by default set to 1. For this example, the factors are left as 1. Tap the OK button to apply the boundary condition and return to the thermal page. Tap the Clear button to deselect all the nodes. The nodes with the boundary condition applied will be marked. To apply the fixed temperature boundary condition to the nodes around the void, toggle on the Group Toggle button. Tap a point inside the section, but close to the void. Create a band by tapping at multiple points within the section and around the void. To close the band, tap on the Select button. The selected nodes around the void will be highlighted. Tap on the boundary icon to access the Node Boundary Conditions page. To delete the boundary condition from the selected nodes, tap on the Delete button. However, when new boundary condition is applied to the selected nodes, it is not required to delete the current applied boundary condition, as the new boundary condition applied will replace the current applied boundary condition. For this example, a node temperature of 100 degrees Celsius will be applied to the selected nodes. From the exposure type selector, select node temperature. Enter a temperature of 100 in the applied node temperature field. Tap on the OK button to apply the node boundary condition. Tap the Clear button to deselect all the nodes. The nodes with the boundary condition applied will be marked. To check the boundary condition of a node, toggle off the Group Toggle button and ensure that the Node Toggle button is on before selecting a node. The boundary condition applied to the selected node will be shown in the node data. Tap on the Clear button to deselect the node. To change the material properties of a mesh or a number of meshes, select the mesh by tapping a mesh when the Group Toggle button is off, or meshes using the band when the Group Toggle button is on. For this example, we will select a group of meshes. Toggle on the Group Toggle button and toggle off the Node Toggle button. Double-tap the mesh text in the Mesh Toggle button to show the material number of each mesh. If the mesh number is shown, then any void with material number of 0 will be selected by the band. To select only material number for non-void elements, double-tap the mesh text in the Mesh Toggle button to hide the material number. Tap on a point on the chart and start to create a band around meshes for the material properties to be changed. Tap the Select button to close the band. The selected meshes will be highlighted. At the same time, the mesh icon will change to the M icon. Tap on the M icon. A dialog box will appear showing a default mat number of 0 representing the void. Enter 2 to replace the mat number of the solid element with mat 2 material properties. Tap the OK button to proceed and return to the thermal page. In the thermal page, tap on Clear to deselect the selected meshes. Note that the material number of the selected meshes has changed. With the Group Toggle button on, tap on a point on the chart and create a band around the section to select all the meshes. Tap on the Select button to close the band. The selected meshes will be highlighted. Tap on the M icon and enter 1 to assign all meshes with material number 1. Next, to specify the surface temperature profile, tap on the plot icon to access the exposure profile page. The exposure profile page consists of the surface temperature profile, radiation factor profile and convective factor profile. The surface temperature profile, radiation factor profile and convective factor profile are set to a default value of 1. If the radiation temperature profile and convective temperature profile are the same, leave the radiation factor profile and convective factor profile as the default 1 and specify the applied surface temperature profile. If the radiation temperature profile and convective temperature profile are different, leave the applied surface temperature as the default 1 and specify the radiation factor profile and convective factor profile. For this example, the radiation temperature profile and the convective temperature profile are the same and hence the applied surface temperature profile will be specified. Tap on the Applied Surface Temperature button to access the surface temperature page. The applied surface temperature can be entered manually or using an expression. To manually specify the applied surface temperature, enter the temperature in the time and temperature fields and tap the plus icon. For this example, a constant temperature of 500 degrees Celsius will be specified. Enter each of the following time and temperature and tap the plus icon. 0.1, 0 and 500. 0.2, 5,400 and 500. It can be seen that a maximum time of 5,400 seconds is specified. The maximum time should be equal or greater than the simulation time. To modify a plot, toggle on Modify. The plus icon will change to the eraser icon. Select 0.2 and enter 70, 200 and 500 in the time and temperature fields. Tap on the eraser icon to change time. To save a surface temperature profile or open a saved file, tap on Files to access the exposure files. Tap on Save and enter a file name of Test Profile and tap Save File. Tap on the cross icon to return to the surface temperature page. Tap on the New button to delete all the data. To open the saved file, tap on Files and tap on the test profile and tap on the Open button. Tap on the New button to delete all the data. Next, the surface temperature profile will be specified as an expression. Tap the expression text to access the expression page. In the expression page, the expression can be manually entered or pre-built expression selected under predefined. For this example, the expression will be manually entered. In the temperature expression, enter an expression of 500 plus T at second, T at second. The time variable must be entered in any expression. The time variable can be expressed as T at second, T at minute or T at hour for second, minute and hour respectively. Tap on the temperature expression text to access the expression guide. Tap the back button to return to the expression page. Where calculated temperature needs to be limited, the minimum and maximum temperatures can be set. Tap the OK button to return the surface temperature page. Leave the time ranges from 0 seconds to 14,400 seconds. Leave that the time interval is 15 seconds. Tap the Plot button to plot the expression. It should be noted that if the expression is not plotted, it will not be used in the analysis. A dialog box will appear notifying that any current plot will be deleted. Tap the OK button to proceed. Double tap on the time text above the time field to change the time to minute. Double tap on the temp text above the temperature field to change the time to hour. Double tap on the point ID text above the point ID field to change the time to second. Tap on any point on the chart to show the plot at any time step. Tap on the Close button to return to the exposure source page. The method to enter the radiation factor profile and convective factor profile is the same as the steps for the applied surface temperature profile. For this example, the radiation factor profile and convective factor profile will be left as a default one. Tap the Close button to return to the thermal page. Tap on the desktop icon to access the simulation data page. In the simulation data page, it can be seen that the solver is set to transient due to the input information. Where the radiant exposure and exposure profile are specified, the solver will be set to transient. Enter a runtime of 3,600 seconds. Leave the configuration factor F sub 12 as 1. Change the emissivity of the exposure source epsilon sub E to 0.5. Leave the convective heat gain coefficient of the exposure source H sub E as 25. Leave the convective heat loss coefficient of the exposure source H sub E as 4. Leave the emissivity of the environment as 0.8. Leave the convective heat gain coefficient of the environment H sub A as 4. Leave the convective heat loss coefficient of the environment H sub A as 4. Leave the ambient temperature of the environment T sub A as 20. Tap Return in the device keypad to access the time history plot. In the time history plot, leave the plot interval as 30 seconds. Note that only up to 5 nodes can be selected for the time history plot. Tap a node to select the node. Tap the node again to deselect the node. To deselect all selected nodes, tap on the Clear button. Tap on a node to select a node to plot its time history. Tap the OK button to apply the changes and return to the thermal page. In the thermal page, tap on the play icon to run the analysis. A dialog box will appear asking the user if they wish to run the heat transfer analysis. Tap OK to run the heat transfer analysis. The results page will automatically show up after the analysis is completed. Otherwise, tap on the thermometer icon to access the results page. Note that the runtime in the results page is showing the runtime chosen, meaning that the transient solver was used. Tap a node in the model to obtain the temperature of the node at the end of the runtime. Tap the scissor icon to slice the temperature plot horizontally and vertically. Tap on the horizontal and vertical slice charts to obtain the temperature at a particular location. Tap on the uptrend chart icon to access the time history page. Tap the items in the list to plot the time history plots on the chart. Tap the selected items in the list again to hide the plots. Double tap the X text to change the time to minute. Double tap the Y text to change the time to hour. Double tap the node ID text to change the time to second. Tap on the Close button to return to the results page. In the results page, tap on the Close button to return to the thermal page. Next, this project will be saved as a saved file. In the thermal page, tap on the Files button to access the Data Files page. In the Data Files page, tap the Save button and enter a file name of test file. Tap on the Save File button to save the file and return to the Data Files page. Tap on the cross icon to return to the thermal page. Tap on the New button to start a new project. A dialog box notifying that all current data will be deleted will appear. To cancel the Create New action, tap on the Cancel button. In this example, we will proceed to create a new project, therefore tap on the OK button. To open the file that was saved earlier, tap on the Files button to access the Data Files page, tap on Test File and tap the Open button. Toggle on the Thermal Toggle button and toggle on the Mesh Toggle button. Tap on the play icon to run the heat transfer analysis, a dialog box notifying that there is potential error with the materials. Please note that this does not mean that there are errors, but to notify the user to check the stability of the model in the Mesh Properties page. Tap the OK button to close the dialog box. Next, tap on the Mesh icon to access the Mesh Properties page. Check that there are green ticks under the solid material properties. The other materials are not used and therefore there is no need to check for stability. Tap the OK button to return to the thermal page. On the thermal page, tap on the play icon to run the analysis. A dialog box will appear asking the user if they wish to run the heat transfer analysis. Tap OK to run the heat transfer analysis. The results page will automatically show up after the analysis is completed. Tap on the Close button to return to the thermal page. Next, the steady-state solver will be used. This would require the radiation exposure component to be removed. For the steady-state solver, the mesh will be made coarser to reduce the run time. Tap on the Mesh icon to access the Mesh Properties page. In the Mesh Properties page, tap on the Mesh Configuration button to bring up the Mesh Configuration page. Enter a mesh size in the X direction and Y direction of 6. Leave the mesh symmetry as about Y and X axis and selected mesh size as modified mesh size. Tap on the Generate button to apply the changes and return to the Mesh Properties page. Check that there are green ticks under the stability check for the solid material properties. Tap on the OK button to return to the thermal page. Due to the change of the mesh size and requirement to remove the radiation exposure component, the node boundary conditions will be reapplied. Toggle on the Node Toggle button to show the external nodes. Toggle on the Group Toggle button and double-tap on the group text to select all the nodes shown. Tap on the Boundary icon to access the Node Boundary Conditions page. Leave the exposure type as Surface Temp but change the exposure profile to Ambient Temperature. Then, set the radiation gain and radiation loss to No. Tap on the OK button to apply the node boundary condition and return to the thermal page. In the thermal page, tap on the Clear button to deselect all the nodes. With the Group Toggle button on, select the nodes around the void with a band and tap Select to complete the band. The selected nodes will be highlighted. Tap on the Boundary icon to access Node Boundary Conditions page. In the Node Boundary Conditions page, change the exposure type to Node Temperature and enter a value of 100. Tap on the OK button to apply the node boundary condition and return to the thermal page. In the thermal page, tap on the Clear button to deselect all the nodes. Tap on the desktop icon to access the simulation data page. The transient and steady-state solver options will be available. Tap on the Steady-State Solver tab. Leave the convective heat gain, loss coefficient H sub as 4. Note that only one convective heat coefficient is specified for the steady-state solver. Leave the ambient temperature of the environment T sub as 20. Leave method as the Gauss-Seidel method. Tap the OK button to apply the change and return to the thermal page. On the thermal page, tap on the play icon to run the analysis. A dialog box will appear asking the user if they wish to run the heat transfer analysis. Tap OK to run the heat transfer analysis. The results page will automatically show up after the analysis is completed. Otherwise, tap on the thermometer icon to access the results page. Note that the runtime in the results page is showing the infinity symbol, meaning that the steady-state solver was used. The G before and S after the infinity symbol indicates that the Gauss-Seidel method was used. When the Gauss-Jordan method is used, G before and J after the infinity symbol will be shown. Tap a node in the model to obtain the temperature of the node at the end of the runtime. Tap the scissor icon to slice the temperature plot horizontally and vertically. Tap on the horizontal and vertical slice charts to obtain the temperature at a particular location. That is the end of the tutorial for the HeatCond2D app. There will be other tutorials using the app containing heat transfer examples that will be made available. Thank you for watching this tutorial.